Hi everyone, we're going to continue with alternating series. This time we're almost there. We have three more tests, the alternating series, the ratio test, and then the root test. These are very similar and they are in our cookbook, part of the series test. I'll go over the list again and fill it in with all the tests. So the alternating series is kind of what it says. So we have an alternating series has the form summation -1 to the n of a sub n. So you have this pattern of you go -1 to the n. So wherever that starts, if it starts at 0 or at 1, that's the n you play in. And so you may start with a negative first or with a positive. So here are some examples. This one starts at 0. So when n is equal to 0, you have -1 to the 0, which is +1. So you have 1, then -1, +1, -1. And so this is what makes it alternating. You're going from a positive to a minus, from positive to a minus, and so on. Second example is this -1 to the n plus 1. Here we're starting at 1. Oftentimes, if we want the first term to be positive, we may adjust this n so that it's either n plus 1, you may see it as n minus 1 as well. Just depending on where we're starting. If we want that first term to be positive, if we don't care, we can just leave it as n. And so this will be -1 to the 1. And so that will be a -1. And so we will start that way. So by conventional notation or conventional form, we usually want our first term to be positive. So we may need to adjust our start time at 0, 1, or 2, depending where we are, so that this first term is positive. So this one, the 1 over n, so it essentially just alternates. So it goes 1, -1/2, +1/3, -1/4, +1/5, and so on. The -1 to the n plus 1 or -1 to the n is just telling you how the sign will alternate. So just like with any series, we want to know, do they converge? What has to happen for an alternating series to converge? And so that's where the alternating series test comes in. So if we have an alternating series, and this one you might think like, well, isn't this just a look at it problem? Yes and no. So I have it under the cookbook because we have some conditions to check. We can easily spot an alternating series because it'll have the -1 to the something, right? n plus 1, n minus 1. That's how I can tell that it's alternating. And then we'll have the formula, the a sub n term. And then in this case, n starts at 1. And so we have n plus 1 so that our first term is positive. So positive a sub 1 minus a sub 2 plus a sub 3 minus n, so on and so forth to infinity. So if an alternating series satisfies these two conditions, a sub n is decreasing. So notice that a sub n, when we talk about a sub n here, we're talking about the part outside of the sign. So the sign, the -1 to the whatever that is, just helps us identify it as an alternating series. Now that I know, okay, that's alternating, now I'm going to focus on the a sub n and then check if that portion satisfies these two conditions. So if it is decreasing, and similar to how we did the integral test, you want to show either doing it this way, showing that a sub n is bigger than a sub n plus 1, meaning the next term, right, the a sub n plus 1 is the next term, is smaller than the previous term. That will tell us it's decreasing, or you can provide a graph. Use a graphing calculator or go to Desmos and graph it. And then the other condition to satisfy is that if the limit as n goes to infinity of a sub n is 0, then we can say that the series converges. Alright, so it converges if these two things are satisfied. So looking at one of the examples up here, so let's look at, well, this one, notice that this we can tell right away that it is not going to converge, right? The limit as n goes to infinity of negative 1 to the n. Well, there's an even, so n in this case, or a sub n will be just 1. So this is not going anywhere. So it is not going to 0. So with this, almost by the divergence test, we can say it diverges. By here, we can say that by the divergence test, because the limit is not 0. So it's not because it didn't meet one of the conditions of the alternating series test. So if the first condition is not met, right? So if it's not decreasing, then the test just fails. If the terms don't go to 0, then we can say it diverges, but it diverges because of the divergence test, not because the alternating series test failed. So the second example, so let's look at this one. Right, I can tell that it is alternating because I have the negative 1 to the n plus 1 and then my 1 over n. So we look at, I know it's alternating. This little negative 1 to the exponent tells me that this is alternating. And that, all that says is, okay, you can use the alternating series test. So we go look at the conditions. So a sub n is 1 over n. So we ask ourselves, is it decreasing? My D looks a little funky here. Is it decreasing? Right? Is a sub n greater than a sub n plus 1? In our case, 1 over n, so is 1 over n greater than 1 over n plus 1? Yes, right, the bigger the denominator, the smaller the fraction. So this is true, so we can say it's decreasing. So yes, decreasing. Does the limit as n goes to infinity of 1 over n go to 0? Right, this is the second condition. The limit as n goes to infinity of a sub n goes to 0. As n goes to infinity, does 1 over n go to 0? Yes. So both conditions are met, so we can say the alternating series converges by the alternating series test. Always, always tell me by what test you're saying that this converges. Notice that this one is without the alternating. This is one that we did in class the other day, just series without the alternating part. We saw last time that this diverges. This is a p series with p equals to 1. So this on its own diverges, but as soon as it goes alternating, now it converges. And so that's kind of one of those nice things about the alternating series. And if we were to graph this one, right, we would have, you can plot those points, so you will go 1, positive 1, then negative 1/2. I don't have room to do that here. I missed the board. Let me see if I can squeeze it in here. So if I was going to graph it, right, it will go at n equals 1, it will be 1 at n equals 2, it will be negative 1/2 at n equals 3. You will have 1/3 at n equals 4, negative 1/4. So you can kind of see how it goes, it gets close to 0, but because you're going positive, negative, positive, negative, positive, negative, they start to add up and they close in on a number. So the alternating series allows it to do that, whereas the regular series didn't. This is the one that we did in class, that it was the consistently adding a number bigger than 1/2, bigger than 1/2, bigger than 1/2, if you recall from class. Whereas this one, you end up getting now close to 0. So it will converge. Okay, next example. Converge or diverge. And so here I can see the negative 1 tells me that it is an alternating series. So this part tells me I can use the alternating series test. And that's really all we use that for. It just helps us tell that I can use the alternating series. And so now I go, my a sub n is 1 over 3 to the n. So the question is a sub n decreasing? Right? Is 1 over 3 to the n bigger than 1 over 3 to the n plus 1? And again, the bigger the denominator, the smaller the fraction. So in this case, 3 to the n plus 1 is bigger. So this is going to be a smaller fraction. So that inequality is good. So then that's true. It is decreasing. You could also graph on your calculator y equals 1 over 3 to the x and on 0 to infinity and see what it does there. Is it decreasing? And you should see that it decreases. And that's 3 to the x, not 3x. And then does the second condition, does the limit as n go to infinity of 1 over 3 to the n go to 0? As n goes to infinity, 3 to the infinity, that gets really large. 1 over a really large number does equal 0. So yes. So both conditions are met, so we can say the series converges by the alternating series test. And so this is why I call it a cookbook. Like as long as you follow the recipe, right? I see, oh, I have a -1. That means I can use the alternating series test. Alternating series test has two conditions to check. Is it decreasing? Do the terms go to 0? If both of those are yes, then the series converges. If one of them fails, if the first one fails, the test is inconclusive, so you have to use something else. If the second one fails, then the series diverges, but it diverges really because of the divergence test. Let's look at the next example. Sorry, I feel like I have to cough. Okay, this next example, and always kind of make sure that our domain is okay. So this, notice that n starts at 2 because 0 or 1 will make this undefined. We don't want to have series are not like improper integrals that we can try to split them up. Let's try to keep at least the bottom limit so that everything makes sense. No undefined at both ends here. Okay, so the -1, this tells me this is alternating, so I can use the alternating series test. What's our a sub n in this case? A sub n is the thing without the negative. So once you notice that it has a negative, great. That's just what tells me I can use the alternating series test. After that, you can kind of forget it. So a sub n is 1 over n times ln of n. And so I have to check, is it decreasing? So is a sub n bigger than a sub n plus 1? I guess that should have been an is, not does. So is a sub n greater than a sub n plus 1? This essentially is telling me a sub n plus 1 is the next term, right? Is the next term smaller than my original term? So if a is 10, right, then this will be is a sub 11 smaller, and then a sub 12, and then a sub 13, a sub 14. So it's the next term smaller than the one before it. So that's what this is asking. If the answer is yes, that means it's decreasing. So 1 over n ln of n, is that greater than 1 over n plus 1 ln of n plus 1? And the answer is yes, right? The bigger the denominator, the smaller the fraction. So this one checks right away. Sometimes the function might be, or the formula might be harder to see. Then graph it on your calculator and see on the interval 2 to infinity, does it decrease? What's the second condition? Does the limit as n goes to infinity of a sub n equals 0? And so in this case, our a sub n is 1 over n natural log of n. As n goes to infinity, both of these are getting really large, so 1 over a really large number is in fact 0. So we can say converges. by alternating series test. So you might be thinking like, so do they all converge? Not necessarily, but also one of the things we may want to know, because things seem to be converging a lot, is a question you may be asked to find is, does it converge absolutely? So does it converge absolutely? So what that means is, does the absolute value of the series converge? And there's the absolute convergence theorem that says that if the absolute value of the series converges, then the series converges absolutely. And so in this case, we would want to look at the absolute value of negative 1 to the n, 1 over n ln of n. And so what the absolute value does is essentially gets rid of the alternating part. So I'm looking at the series 1 over n ln of n. So that's this converge or diverge. And we're going from 2 to infinity. So now what do we do with that? Now it's no longer alternating, so we have to use a different test. So we already know the limit goes to 0, so divergence test doesn't work. It's not geometric, it's not p-series, right? Because it's not just 1 over n to the p. We have that ln of n there. But I do have an n, so I could try to compare it. So I could use comparison test. I could also notice that ln of n was the derivative of natural log n, 1 over n, right? So here I could use the integral test. I already know from doing the regular alternating series test that it is decreasing. The other part is to check, is it continuous on 2 to infinity? Yeah, this is only undefined at 0 and at 1, but that's not on our interval, so this will be continuous. So if I want to use the integral test, we let f of x be 1 over x ln x, and then see this is continuous, and it is decreasing, and it is of positive terms. And so we can look at the integral. So the integral of 1 over x ln x dx, we can do it using u substitution. Right? Let u be ln x, du is 1 over x dx. So this becomes the integral of 1 over u du, which then will be integral of 1 over u is natural log of u. I'm going to cut some steps here. U was ln of x, so from 2 to infinity. Notice that since this is going to go to infinity, ln of infinity is infinity, and then ln of infinity again, that's still going to be infinity. So this is going to go to infinity. So the integral diverges, so that means they both diverge. So the integral and the series both diverge by the integral test, which means this diverges. So does it converge absolutely? No. So then because the absolute value of a sub n diverges, I can say the series, my original series, converges conditionally. And the conditionally comes from, it did converge when it was an alternating series, but once I took the absolute value diverged. So then I say the series converges conditionally. Had it converged here, then the alternating series converges and the absolute value converges, then we say converges absolutely. If you do it on your own for this one up here, this should converge absolutely, because if you get rid of the negative 1 to the n, this is a geometric series with r equals to 1/3, less than 1, so it's going to converge. So this one will converge absolutely, And if you look at this one, we already know that this one diverges, the absolute value diverges, but the alternating series converges, so this converges conditionally. So that's another layer to the alternating series test. Let me record a different video for the estimation theorem.